Welcome to qnawire.
Our question says that we have three long parallel wires with lengths L of 3.5 centimeters or 0.035 meters, each carrying a current I of 8.0 amperes. So looking along them, they are at the three corners of an equilateral triangle, but the directions of wire M is opposite that of wire N and P. So you can look at figure 54 to get an understanding of this. And it's asking us to determine the magnetic force per unit length on each wire due to the other two. Okay. So the force per unit length between any two wires is calculated by the formula that says that the force over the length is equal to mu naught times the current in the two wires, but the current is the same in both. So the current in the two wires is just going to get squared, divided by, and this is mu naught, magnetic permeability of free space, divided by 2 times pi times the length L. Okay, so now that we have the equation for the force per unit length between any two wires, so we can use this to apply it to all 3 points, and we can calculate the total magnetic force per unit length. So the current, again, we have the current in each wire written, the length of each wire written. So if we plug in the values into this expression, remembering that mu naught is 4 pi times 10 to the minus 7 Newton per meter squared, we plug those into this expression, and we find that this comes out to equal 3.66 times 10 to the minus 4. And of course, since it's force per unit length, the units here are going to be newtons per meter. Okay, so now we can find the force acting at the different points, M, N, and P. So let's go ahead and find the first one. At point M, F of M is going to be equal to the force on M from P times the angle at which this force is applying, and that's going to be 30 degrees. So this is going to be the cosine of 30 degrees. And then we're going to add to this the force of N on P, and then times the angle, and it's the same angle, cosine of 30 degrees. But these forces are not just forces in newtons, but forces per unit length. Since these forces are equal and the angles are equal, we can go ahead and add them together. So we have 2 times F over L that we found above, because it's the same in each case, right? Because each one has the same current that's acting on it. So it's 2 times F over L times the cosine of 30 degrees. So plugging those values into this expression, we find that the force on M is 6.33 times 10 to the minus 4. And the units here would be newtons per meter. And this is at an angle of 90 degrees. So we can say this is at theta equals to 90 degrees from the image. And we can go ahead and box that in as our solution to the first part, the force on M. So we're going to do the same thing now for the points N and P. So the force on the second one on point N is going to be equal to the force from M and N times the angle at which this force is acting, which is 60 degrees, or the cosine of the angle in which it's acting, which is 60 degrees, plus the force N and P times the cosine of the angle at which they're acting, which is also 60 degrees. Okay. Well, again, these two forces are equal, so this is 2 times the two forces, which we found, F over L, because this is, remember, force per unit length here, times the cosine of the angle 60 degrees. Okay, so plugging these values into the expression, we find that F sub N is 3.66 times 10 to the minus 4 newtons per meter. And this here is at an angle of 300 degrees. So we can say this is at theta at let's rewrite that to make it look a little neater. Sorry about that. So this is at theta equals to 300 degrees. And we can box that in as our solution for the second part. And then the very last one is finding the force at point P here. So the force on P, we'll call this F sub P, is going to be equal to the force from M to P times the cosine of the angle. In this situation, from the figure, it's 60 degrees. So this is multiplied by the cosine of 60 degrees plus F P to N, which is going to get multiplied by the force angle, which is 60 degrees. So cosine 60 degrees. Again, the forces are the same, so we end up with this 2 times the force per unit length, which is just F over L, which we found in the beginning, times the cosine of the angle, which was 60 degrees. So if you look closely, this is the exact same as above, so we're getting the exact same solution that we just got for the point N. And so this is 3.66 times 10 to the minus 4 newtons per meter. Except this time we are operating at an angle of 240 degrees, or you could also call it negative 60 degrees, but we'll just say 240 degrees to make it easy. So at angle theta equal to 240 degrees. We can box that in as our final part of the solution to our question.